Should be going live soon. And I think we are live. Cool. We're live and well. So hello everyone. Welcome to the OneClass channel. My name is Millan and I am a software engineering student at Carleton University in Ottawa, Canada. Today we'll be going over some commonly asked mathematics questions at both the high school and college levels. And if you need some help tutoring or with your homework, check out the links in the description below. Alright, so let me switch my screen over to our first question. Okay, so here we go. The first question that we want to deal with today is, what is the derivative of log x? Let's write that out in a more mathematic type language. So let's draw it out. D over dx, meaning we're taking the derivative of log x. Now, how do we deal with this? Well, this is one of those differentiations that you're kind of going to need to really keep on your tool belt real nice and handy, because it is likely that you will see this rather commonly. But the result of this is we are going to do 1 divided by the logarithm, the natural logarithm of the base multiplied by what's inside. Like, what I mean by inside is like inside here. And then we need to multiply this whole thing by the derivative of what's inside because of the chain rule. Don't forget the chain rule. Okay, so a good thing to note is that with logarithms, we're often going to see a base most of the time. Let's call that base b. This base b is what is going there for your information. Now, if the logarithm doesn't specify a base, so we just have log here, like log no specified base of x, what that means is we have to assume base 10. If there is no specified base, assume base 10. Okay, so in the question that we're giving, we have no specified base, meaning that we have a base 10 situation right here. So this equation is good, but let's do this, but with the example that we have here with base 10. So the derivative of logarithm x is equal to 1 divided by the natural logarithm of 10, that's the base, multiplied by x. Here, because of the chain rule, we got to multiply with the derivative of what's inside here, but we know that the derivative of x is just 1. So this entire thing here, that simplifies out to 1 in this case. So we actually don't need to write anything for that. And this would be our complete solution right here. The derivative of logarithm of x with no specified base of the log, that means we're assuming base 10, the result of that is 1 divided by natural logarithm of 10 multiplied by x. Now, something I want to mention is that, let's say we had a different base that looked like this. Log maybe base 2 of x. Send that through the differentiation, and we will have 1 over natural logarithm of 2 times x. Okay, that makes sense. It follows the rules. But something I want to mention. A ln, or natural logarithm of x, is equal to regular logarithm with base e, which you could also write as like natural logarithm or logarithm of 2.718. It's a big long number. When we do this, we know that the derivative of natural ln of x, that is going to be following our log strategy here. We have the result of that is 1 divided by natural ln of the base. In this case, the base is e. E stands for Euler's number, from a guy named Euler a long time ago. He was trying to figure out compound interest calculations, and that's how he figured out what e was. Fun fact. And then multiplied by x. Send that through your calculator and tell me what you get. Natural logarithm of e, which is the base, is 1. So that's equal to 1. So this is just 1 over x, which is why the derivative of natural logarithm is 1 over x, whereas the general rule for taking the derivative of a log, regardless of the base, is 1 over natural log of the base times x on the denominator. Yeah. So to verify the solution that we have here on OneClass, yep, they got the general formula for logarithm. You put the natural log on the bottom of the base multiplied by what's inside, and of course they would have like the internal derivative of the argument to log if this was something more complicated than just x. But with base 10, it looks good, so we can approve this solution. The above solution is correct. Cool. Super. Okay. So let's clear out the whiteboard and let's get it moving to our second question. We have, what is the antiderivative of e to the power of negative x? Antiderivative is a fancy way of saying integral. In the same way that you could say the anti-integral is the derivative, but people don't typically say that. Anyways, the antiderivative is equal to the integral, which means that this question is essentially asking us to take the integral of e to the power of negative x dx with respect to x. Okay, so let's think for a moment. It tells us antiderivative, so that kind of gives us a hint of how we could handle this question if, let's say, we didn't know what the integral was. So we got to find d by dx of, let's call that square, is equal to e to the negative x. Now we know that to take the derivative, e to the x derivative is e to the x. or I'll say it like this with the chain rule, because we do have a -1 factor in front of that. So let's say we have d by dx of e to the f of x. That is equal to e to the f of x. The power is unchanged, multiplied by the derivative of the power. You see how the power is f of x here? You multiply the whole thing by the derivative of that. So we see that here the derivative of this, like the power is never going to change between differentiations. So we know that its previous thing that we started from is actually, let me move some things around. Whoops. Technical difficulties, my bad. Yeah, just gonna move this like over here. Okay, technical issues resolved. We know that we are going to get d to the dx of something. Let's just call that a for now. Multiplied by e to the negative x is equal to e to the power of negative x. Sounds good? So basically we're trying to find what a is so we can find the original. So if we do this, we know that we can just like move out the constant a in front. D over dx of e to the negative x equals e to the negative x. Let's take the derivative of this. So that would be, with our little chain rule up here, we have a as our mystery factor before, because we're basically trying to solve for that, times e to the power of negative x times the derivative of negative x, so that's -1. Derivative of the negative x, that's the power, is equal to e to the negative x. Okay, now let's expand this out. So we have negative a times e to the negative x equals e to the negative x. We're solving for a. And we know that for this to be true, we conclude that a is equal to -1. Meaning in here and here, let's put these puzzle pieces together. We get negative, or d over dx of negative e to the power of negative x is equal to e to the power of negative x. Looks about reasonable. And of course, like if we followed the calculation, we would find that these two are equal. So when we found, we're looking for the antiderivative. So basically that's just saying, find something that where you take the derivative, you will find e to the negative x. We found that the result of that is negative e to the power of negative x, which is the same as what you would get with the integral. The integral is just like a more formal way to say it, but a lot of the times when you're just being introduced to the idea of integrals, some people would like to call them antiderivatives, because it is very important to know that integration and derivatives are opposite operations of each other. Kind of like how multiplication and division are opposite operations of each other, derivatives and integrals are opposite operations of each other. And that is actually the fundamental theorem of calculus. It's very important to know. So reading through the solution that we get here on OneClass. Actually, an important thing that we need to know is that like with the antiderivative, it does work, but if we were to say integral, we would be more important to have a plus c constant here. So instead, we'd want to have like d over dx, negative e to the power of negative x, plus constant of integration equals e to the negative x. Now, the reason why we need this constant of integration is like, let's say we have negative e to the power of negative x, and let's say c is like, you know, a nice friendly constant number like 21. If we take the derivative of that, like we'll take the derivative of both these terms individually, the constant is going to zero itself out and it's not going to appear in the next term. But let's say if we're taking the integral once, let's say we need to take the integral again, like this c would come from something that's higher order. So that's why we need to have the constant of integration when we take the integral. But I suppose when they're asking for antiderivatives, that's like less explicit. When you're asking for integrals, always make sure you got the plus c. If you don't see the c, you're going to see some d's on your report card. So, you know, it is what it is. Don't forget the c's. Okay, let's verify the solution here so we can say the above solution is correct. Nice. Let me just clean up our whiteboard here. Our whiteboard. Solution is good. Cool. So we can move on to the next question that we have on the menu today. The next question that we have on the menu today is, what is the area of a semicircle? Now first, we got to think about something. What is a semicircle? Here we have a circle. I'll try to have a straight line. Chop that circle in half and you get a semicircle. I'll just color in the part that we're trying to figure out. Okay, so that's semicircle. Beautiful. So we got to find that area. So, what would be an easy way to think about this? I already mentioned a semicircle is just a regular circle chopped in half. So would it be reasonable to then say that area of semicircle equals area of circle divided by 2. That sounds about right. If we had the whole area, divided that in half, we'd get the area of half of it. So that'd be the area of the semicircle. That's cool. Cool. So let's rewrite area of a circle. That's one of those trusty equations that you're probably going to need to remember. And you're going to know that it is pi r squared. And we got to keep the divide by 2. Now, what is r? R, radius of circle. Now, what is the radius? The radius is, hey, it kind of looks like a Pokeball. The radius is the distance between the center of the circle and the edge of the circle. And radius is the same no matter which direction it is. Like the radius here, the radius there, always the same radius. So if we have the radius, we could figure out the area. So let's make this, let's call that AOS, area of semicircle, is equal to pi r squared over 2. But let's say that our semicircle, let's see if I can draw one actually. Okay, looks like I'll have to draw it by hand. Let's say we get a semicircle. You know, someone gives us half a pizza or something like that. Or like, you know, someone cuts your skateboard wheel in two. And you can only figure out here. You can only figure out that. That is called the diameter. And sometimes with circular type things, it is easier to measure the diameter than it is to measure the radius. An example of that is like, let's say you have a cup, the opening of a cup. Diameter, you measure like, okay, the side to side length. To measure the radius directly, that's a little bit more difficult because you got to be like, okay, I have to find the perfect center of like, you know, the opening of the cup. The distance from the perfect center to the edge, that's going to be the radius. Well, it's difficult to find out exactly where the perfect center is. So in some applications, finding the radius, the diameter instead of the radius is going to be easier. So, hey, wait a minute. If we know that that's the center, and that's R, that should be R as well. So we know that diameter is equal to D, but is also like D just as a symbol because we don't want to be writing out diameter every time. D as a symbol, diameter, is equal to 2 times radius. Interesting. So let's see if we can input that into here so that we have a different equation that can help us if we're only able to find the diameter. And there are some real world reasons why that may be the case. So we can use the same equation, like we got pi over 2 multiplied by, let's isolate R from here. So R is equal to 1/2 diameter. So we'd have 1/2 diameter in here, taking the place of where R used to be. But R is squared. So this entire unit, 1/2 D, needs to be squared. Okay, let's expand that out. We got pi over 2 multiplied by 1/2 D squared is the same as D squared over 2. Over 4. 4 being 2 squared. So basically you're just like, okay, squaring the top. So that's the D squared. And then you square the bottom. The 2 squared becomes a 4. Okay. So let's, compress this even more. Like we can multiply the 2 and the 4 on the denominator together. So we can get pi times D squared divided by 8. That is equal to pi times radius squared divided by 2, which is the area of the semicircle. Pi, by the way, if you're unfamiliar, is 3.1415926, and it goes on and on. It doesn't really make that much sense for you to memorize more than like 5 digits of this because normally you're going to be using your calculators anyway to get this number. But just for your reference, if you don't have a pi button on your calculator, you can you're typically good with just going with like 3.14 typically. But yeah, that would be exactly how we find the area of a semicircle. And it would seem that the solution that we have here on OneClass definitely agrees with us. So we can verify that. The above question is, or the above is correct. Cool. Let's clear this out. And let's get it moving to the next question on the menu. So the next question is, what is the derivative of absolute value functions? Well, first, let's talk about what even is an absolute value function. You might see them, typically you're going to see them as vertical bars like this. So like x. Or sometimes you might see them like this, like abs. Typically like this. What this means is that if negative, make positive. If positive, keep positive. It's basically just saying, if you're negative, we're going to multiply you by -1. If you're positive, you're good. Sounds good? All right, so let's say we have a relationship. Let's say we have it like y equals the absolute value of x. Let's think about what this would look like graphically. So we have our x-axis here, our y-axis here. Let's call this like 1, 1, -1. Okay, so let's start at 0. Like when x is equal to 0, y is equal to 0. Sounds about right. When x is equal to 1, y is also equal to 1. Looks reasonable. And if x is equal to 2, y should also be equal to 2. So far, so good. Now, remember what we said earlier. If negative, make positive. So let's say x is equal to -1. We got to make it positive. So it's going to be when x is equal to -1, y is equal to +1. Y being the output of the function. Let's say we have x equals -2. In the same way, y is going to be equal to +2 because the input is negative. The absolute value says if it's negative, positivify. Make it positive. Yeah. So basically we're going to get a function that kind of looks like this. Let's say we have like, I'll do a different color for this, maybe red, like strawberries. Y is equal to 3x. Well, if y equals 1, if x equals 1, y equals 3 times 1, that would be 3. And if y equals -1, if x equals -1, y is 3 times -1, but those are inside the absolute value, so that would be +3 as well. So like, no matter which way you flip it, somehow, some way, these absolute functions, absolute value functions, they kind of got like, this, like they're really excited and trying to show you something big type of expression. Like they're doing the YMCA Y. All right, so how do we find the derivative? Well, we know the derivative is what's tangent to it. And with these, they are like mostly straight lines. So we should expect that their derivatives should be fairly constant. Except that, it depends on like if you're going down or going up. But otherwise, since the line is straight, the tangent line is always going to have the same slope. So we should expect a constant value for the result of our derivative. Okay, cool. So now that we have our some basic fundamental knowledge about absolute value, let's pull out our equation. Equation for absolute value differentiation. Okay, Now, let's say f of x is within these bars here. Like f of x, it could be x by itself. In this other example, we have 3x. You could have pretty complex functions in here. You could even have like multiple functions. But let's just like pretend that is 1 for now. So the derivative of this, d over dx of absolute value, f of x in the absolute value, is equal to the inside on the top, f of x, divided by the inside on the bottom, but that remains in the absolute value. All of this is multiplied by the derivative of the inside. Sounds good? This is our formula for the derivative of absolute value. Keep that handy. Okay, so let's say we have an example. Let's say our most basic example, we have y equals absolute value of just x on its own. Well, following the formula here, we're going to take the inside, just naturally, put it on top of the fraction, x right there. We're going to take the absolute value of what's on the bottom. Oops, let's make that bar a little more straight so that it's clear that we're talking about absolute value here. And we got to multiply it by the derivative of what's inside. So here, we just have x on the inside. The derivative of that is 1. So we just multiply it by 1. And that's about it. So let's see what this means. For x is greater than 0, this is just going to be y prime equals 1. Right? Remember our graph, it was like y, x. It looked like that. When x is greater than 0 and we're on this side, the derivative is 1, meaning that the slope is a constant 1. That looks pretty reasonable. Now let's see when x is less than 0. When x is less than 0, let's say x is like -1. Well, we'll sub that into our equation. -1 divided by the absolute value of -1, that's +1. So it'd be -1 divided by +1. Regardless, you're going to have like the x on the top and the x on the bottom, they're going to divide each other out, but their signs are going to be opposite when we have x less than 0. Because of that, the answer to the derivative of this when x is less than 0 is that it's always going down with the slope of -1. Equals -1 when we're on this side. Looks about reasonable. Now, let's talk about the super special case when we have x equals 0. When x equals to 0, we're basically trying to do 0 divided by 0. Ooh, that divided by 0, that's an issue. That's something you definitely do not want to be doing. So you can't really find the derivative there. Also think about this way, like it's a corner, like this, at the base where x is equal to 0. Because of that corner, like what's the tangent line? Like originally it was like this, and then it's doing here, like it's trying to be both at the same time. It doesn't work out. So just know that there are certain places like corners, sometimes vertical lines are also like this, where it is impossible to actually find a derivative at certain points. Okay, so keep that in mind. This would be like basically your output for the function of absolute value of x. Let's run through another example where we have something a little bit more spicy inside. So like the example that we had previously is like, example, y is equal to the absolute value of 3 times x. All of that's an absolute value. We're going to run this through our equation here. So we have y prime equals to 3x divided by the the absolute value of what was inside. And then we have to multiply this whole thing by the internal derivative of the absolute value. So inside we have 3x, the derivative of that is 3. So the 3 here and the 3 here cancel out. So we get x over absolute value of x, 3x. Just moving the 3 here to the front. Okay. Now let's do a similar type of analysis that we did for the previous one. For x is bigger than 0, x less than 0, x equals 0. X equals 0, we're still going to have the same thing. I guess it would be, you'd write it as not exist. The backwards E stands for exist. Sending a line through it means not exist. If x is bigger than 3, we would have just like no absolute value. Like we would put in something for the x at the bottom here and it would end up being positive. So that would divide out and we would just have 3 prime equals 3. If x is less than 0, meaning that x is negative, we will have this will become negative x because we have to like undo the negation in the bottom because of the absolute value. And then we will have like a negative value up here divided by its positive version of itself. The magnitudes divide out, but there's still going to be a negative on the bottom. Negative on the top. So the result of that is going to be y prime equals negative 3. Now if we scroll up to our little diagram that we had of this, y equals 3x, we can see that makes perfect sense. Like the slope is a little bigger here for the red line where it's 3x. It follows the same pattern, and all in all, I would say that we definitely have found our answer. So the key here is that the derivative of your absolute value is going to be this equation. Keep this equation nice and handy. Because if you ever get asked, hey, what's the derivative of this absolute value function? You're going to know exactly how to deal with it if you got this in the bag. All right. Sounds good. All right. So I can just got to verify the solution. Solution is good because yes, maybe I'll just say above solution is showing the chain rule. That's the reason why we're multiplying the inner derivative, is because the chain rule. Okay, so just gonna clean up the whiteboard and then we can move on to the next question on the menu. So the question we have here is, what function is shown on the graph below? And we have a few options. We have y equals log of base 0.04 times of x, then log of base 1, of base 3, and base 10. Now the question is basically asking us which one of these line up to this little graph that we have. Well, let's write down our points of interest. So we have 3, 1. We have 1, 0. And we have 0.4 paired with negative 0.6. So first thing that we can do is we know that when y is equal to 1, or with logarithms, with logs, when y is equal to 1, x equals base. That is basically just one of the rules of logs. Well, let's first think about what logs even mean, right? Logs is basically like, so we have log of base b of x equals, let's say c. Basically, it's saying the base to the power of x is equal to c. Meaning that we're basically looking for the power here. So when we sub in like let's actually just try to sub this into some of our options here. The one that is looking the most like it would probably fit is log base 3 of x equals y. Let's sub that in and see. So log base 3 of our first point, our x value is 3, equals, our y value is 1. Let's pull out our handy dandy calculator. And we can see that a lot of calculators don't have the functionality for you to set your own bases. So another thing that I want to mention is that log base b of x is equal to log of x over log of base. Now the logs that you have on the top and bottom of here, it doesn't matter what base they are. It's just like because most of the time your calculator doesn't specify which base your log is. That means it's definitely log base 10. So if you're trying to do logs of other bases, you got to use this because you probably won't be able to sub in your own log values. So given that, let's see if 1 is equal to log of 3 divided by log of 3, which is the base. Would you look at that? We got the same thing on the top and bottom, meaning that they're going to divide out and equal to 1, which is exactly what we were expecting. So we know that our answer has to be C, log base 3. Another thing that I was mentioning, like, okay, when I was saying like when y equals 1, x equals the base, that's because when we have something like this, like, how am I going to explain this? It's kind of tough and out of the way for me to explain like with a detailed proof as to why this works out, but generally when you have a graph and you know that it has this logarithmic shape, look for when it's equal to when it has a height of 1. That's probably going to be your base. And then you can use these equations to check it. And honestly, in multiple choice situations like this, it's a perfectly valid move to just like send them all through your calculator, do trial and error. One of them is going to be right. A thing I want to mention here is that there are 2 option C's. So that is something of concern. So to answer this question on the OneClass, the given answer is needs answer is y equals log base 3 of x. Note, last 2 options are both C. Can be found by subbing in the of interest into the different options. Okay, cool. So that would conclude this question. Oh man. Oops. Okay. So the next question that we have on the menu here is, what is the derivative of tan x? It's really asking for us to do d over dx of tan of x. Now I'll tell you straight up that this is something that you might want to memorize to be equal to secant squared of x, which is equal to 1 divided by cos squared x. Now let me show you why this works. So we know that tan of x is equal to sine x over cosine x. It's a little bit complicated to like fully give you a detailed proof as to why this works, but just trust me. Tan of x is equal to sine divided by cos. Okay, so if we were to take the derivative of d over dx of tan of x, that is equal to d over dx of sine over cos. Oops. We got to hit this with the quotient rule. Hit it with the quotient rule because when you have one function divided by another function and you're taking the product of that and the derivative, or you're taking the derivative of the product of that, you have to hit it with the quotient rule, which is d over dx of f of x over g of x is equal to the derivative of the top times the natural bottom, subtract the natural top multiplied with the derivative of the bottom, all over the bottom squared. So given the quotient rule, let's run our function through this. So it is equal to the derivative of the top is sine x. So, or the derivative of sine x is cos x multiplied by the natural bottom, so that's also cos x, minus the natural top, so that's sine x, multiplied with the derivative of the bottom, which the derivative of cos x is negative sine x. Don't forget that negative. So since we're going to multiply negative sine x on this, we can just make that a positive. So plus sine x over the bottom squared. So that's cos of x squared. So let's rewrite this. Like instead of writing cos times cos, we can just have cos squared. Same with the sine. Sometimes instead of writing it like the whole thing in brackets and then squared, you'll see this. This means that like the coses are squared. But stay ready for both notations. Of cos x. Now, an important thing that I want to mention is that 1 is equal to cos squared of x plus sine squared of x. That's a super important trigonomic identity that you most likely want to memorize, because this is very useful in a lot of different situations where you want to simplify things. So we can just replace the entire top with 1, because the cos squared x plus sine squared x, those added together, that's 1, over cos squared of x, which is equal to secant squared of x. And that is how we came to the conclusion of this being the derivative of tan x. So generally, you're probably going to want to memorize the derivative of tan x instead of like going through this entire quotient rule process every time. But otherwise, that's that. Isn't that fun? Derivative of tan x is secant squared of x. I just need a comment in the answer. Secant squared of x is written, should say derivative of equals secant squared of x, or I'll write it this way, d over dx of tan x is secant squared of x. But otherwise, the answer follows the similar pattern of we got to use the quotient, or first we're going to break down tan into sine divided by cos. Send it through the quotient rule. Hit it with the identity on the top. Looks pretty good, but I'm worried about that because those are not equal. So I'm going to mark this as incorrect. And then we can move on to the next question on the menu. So the question asks us, what equation is represented by the graph below? This is the graph below. Let's get at least one point of interest here. My point of interest at when x is equal to 0, I'll write point of interest. Spelling is not my strong suit. When x is equal to, or we have our xy here. When x is equal to 0, y is equal to halfway between 0 and 2, so that is 1. Okay. Now, we got 4 options. This is a little multiple choice thing here. Something that we see is that when x is negative, we still got y values. Like, of course, they're pretty close to 0, but they're still there. That means that we can kind of disqualify these logarithm options from here. Because try taking the logarithm of a negative number. It ain't gonna work out. So if it was a logarithm type graph, we would not even have anything on the left side of x equals to 0. So A and B disqualified from even being considered. So our remaining 2 options is y equals e to the power of x, or y equals e to the power of x plus 1. Let's sub in this point of interest. If it works for these equations, then we'll need to do further analysis, but I got a feeling this should tell us exactly which one of these options it is. Let's start with C, because that's what I see first. So we have e to the x equals y, which means that at the point of interest, when x is equal to 0 and y is equal to 1, that means we should expect e to the power of 0 to be equal to 1. And any number that is not 0 to the power of 0 is 1. So C looks good. To be double sure, let's see what D is, and we should see that D is not going to work for this point of interest. Option D. So we have e to the x plus 1 equals y. And when we sub in x equals to 0, e to the 0 plus 1 equals y equals 2 equals y. Hey, that's not agreeing with our point here. So we know that option D is disqualified. Disqualified. Option D. D stands for disqualification. So we know that our answer has got to be option C. So let's take the look at the answer that we have on OneClass. And I guess with this solution, they're just showing graphically what the other options are. That's a perfectly valid way of figuring out this question too, is just to say, okay, let's plot all these graphs, see which one lines up. And yeah, like I mentioned earlier, like with these logarithms ones, you're generally not going to see anything on the left side of the 0. So because we did see something on the left side of the 0, we could immediately disqualify a lot of the logarithm stuff. Same thing with this one. Because the plus 1 factor, that kind of shifts the entire thing to the left. But even then, you could kind of still see like there is a vertical asymptote at x equals 1 where we will not see the graph go to the left of. Yeah, and then we saw that everything is good when we have y equals e to the power of the x. And when we sub in the point of interest, it does not work out for the other option, which was e to the power of x plus 1. And I guess they use the same method as us, so that's cool. So we can verify that this solution is good. The above solution is correct. Cool. Let's clean up this whiteboard and we can move on to the next question on the menu. Okay. So the question we got here, how to find the derivative of a function? Well, first we got to think about like what even is a derivative? A derivative is a function that tells us the slope of a tangent line of the function that is its integral. So I'll write it as like, tells us slope of tangent line at, or yeah. Now what is a tangent line? A tangent line is basically like, let's say we have a curve here. A tangent line is like, you know, when people say, oh, I'm gonna go off on a tangent, it's kind of like they're going off path. So let's say we have a tangent line at the top here. The tangent line is just like a flat line that pretty much matches like the point that is taken a tangent of. So see here on the top of this curve, you would have like a pretty much flat line. If you were to take a tangent line here, it would be a diagonal line. The derivative tells us the slope. So that's the run, that's the rise, and slope equals rise divided by run. Okay. Another way that we can see tangent line, or the slope of a tangent line, it can also tell us the instantaneous rate of change. So another way you can look at this is like, you know, try this on your own. Go on to like Desmos or whatever graphing calculator you like. Make any function, make it a curvy function you like, but any function, if you zoom in, like really zoom in, it pretty much looks flat. And we're basically taking the derivative means at a certain point we're going to want to you know, find the slope of that area that is pretty much flat when you really zoom in. Okay, so let's say we have a line here. How would we find the slope of this? Well, we would take like, if this is our x axis and this is our y axis, let's say here we have like x of a, and if we call that h, or if we call this distance h, and this is h plus x of a, like you see, like originally we have x of a, go shift over by h and you got h plus x of a. Yeah, so here we have like f of x of a, the result of when you send it through a function, and here we have f of x of a plus h. We're looking for the slope, right? Slope equal to rise over run. Okay, what's the rise? How much does it move vertically? Well, the rise is just like its a final value minus its initial value. So we have f of x of a plus h minus f of x of a. I'm using x of a because like I don't want that to be confused with the x-axis. But like you do see in here, they just use x, but that is not, that doesn't really change much. And on the bottom of this little fraction that we got, we have its destination, where it ends up, divided by or minus where it came from. So we have h plus x of a minus where it started from, and that's just x of a. These two terms zero each other out. So we know that the slope is equal to f of x of a plus h minus f of an x value that we sub in, add yeah, and all of that is divided by h. Okay, so that's how it seems like on a macroscopic scale. But we really want to be zooming in to get as accurate as possible, because like the more you're zoomed out, the less that you can approximate your functions to be straight lines. Only when you like really zoom in, meaning that our h value here has to be really small, and then we can calculate this out. So let's say that we were to we got to find out a way that we can kind of see what this is going to approach as h gets closer and closer to 0. So typically when you're learning calculus, you learn about limits, right? So this is why limits are important. So we want to minimize h. And we're going to do something like this. So we got to find out what the slope is by doing the limit of h as h approaches 0, meaning h is getting super small, and we are getting like a more and more accurate calculation for our slope at that point. So we have f of x of a plus h minus all minus f of x of a all over h as h approaches 0. So this is the definition of a derivative, and that's where it comes from. It's like we're trying to find the slope, and we know our slope equation, and then we want to get this such that to be as accurate as possible, we want h to be like closer to 0. Okay, so let's run this through an example. Let's say that we have f of x. Let's see if we can match the example that they give us. It is 2x squared plus 10x. Plus 10x. So let's sub this into our equation. Instead of using a specific value for x, which would be like an x of a, let's just use a general x. So I'll actually just like erase the subscript a that we have here to specify. That would be like for a specific x. Because if we're trying to find the derivative at a certain point, let's say the derivative at x equals 5, we would sub in like x of a is 5. But instead, we're just going to keep it as a general x. Okay, so what would be f of x plus h? Well, for every time we see x, we're going to put x plus h. That first one is squared. The second one plus 10x plus h. Let's expand this out. F of x plus h. So that's 2 times x squared plus 2xh plus h squared. Right? So multiply that by itself. Add up 2 times, first times second, and then add up the second one squared. And this the next term that we got here, 10 times x plus h, so that's just 10x plus 10h. And let's expand out this first little section that we have here. So that's 2x squared plus 4xh plus 2h squared plus 10x plus 10h is equal to f of x plus h. Okay, now that looks long, but it should not look scary. So we have our f of x plus h, we have our f of x, and h is just what we're going to leave in h. So let's sub all of those into the equation and see where that takes us. Limit x approaches, oops, it's not x approaches, h approaches 0, because we still need x because we need to find derivatives at certain points. The derivative is just going to give us an equation to help us find the slope, but we need to sub in an x value to get the slope at certain values. So the first thing that we have here is 2x squared plus 4xh plus 2h squared plus 10x plus 10h minus the original f of x. We have to put that in brackets. 2x squared plus 10x. All of that over h. Okay, so let's do some quick math to see what we can cancel out. So let's send this this negative 1. Let's just copy this real quick. Okay. So what I did here is I multiplied those last two terms by negative 1. Okay, and you see, okay, we have a negative 2x squared and a positive 2x squared. So those zero each other out. We have a positive 10x squared and a negative 10x squared. So those zero each other out as well. So let's see what we have left that is not zeroed out. Limit h approaches 0. 4xh, that was not zeroed out, plus 2h squared, also not zeroed out, plus 10. 10h, that was not zeroed out, all divided by h. If we look at the top, all three of these terms multiplied by h. How about we factor that out? H approaches 0. We have h 4x plus 2h plus 10h. All divided by h. Oh, look at that. We got h on the top, h on the bottom. Divide them out of each other. And we have limit of h approach 0 of simply 4x plus 2h plus 10. Whoops. That should not be there because it was factored out. My bad. Good thing I caught myself before the catastrophe happens. And then with the limits, we direct sub. We directly sub in h is equal to 0, and we get the result is equal to 4x plus 10. Because this term in the middle, 2h, when we multiply it by h equals 0, that gets zeroed out. So the derivative of so this was equal to the derivative of our original function, which was 2x squared plus 10x. And honestly, if you've seen other methods of finding the derivative, you'll see that like this definitely agrees with that. And to take the derivative like this, it all comes from the fundamentals of like we're trying to find the slope. So we're going to really zoom in. We're going to see like at a certain x value, and then we're going to add a little bit to it. Just go a little bit past that by h. But h, we want it to be very small. That's why we need the limit. We're going to take the slope, and that comes from the rise divided by run. We simplify to get this equation. This is also called the first principles method of finding derivatives. And once you find that, typically you'll be able to sub in your functions and solve and find your derivative. So that would conclude this question, and the answer that we have here on OneClass agrees with us. So we can mark that this question is good and keep it moving. Okay, I'm just gonna clean off this whiteboard. Okay, next question that we got on the menu today. What is the derivative of cosine of x? So to format this as more of like a mathematically looking question, we have basically d over dx of cos of x. Now this is kind of one of those things that you're gonna need to memorize, because it's pretty time consuming to like actually go through this as a proof, but just know that it is negative sine of x. Do not forget the negative. Never forget. If you forget it, well, you're going to be in trouble. But let's also think about this, because the cool thing about sine and cos is that you can keep on taking the derivative over and over again, and you're going to start to see a pattern. So let's take the double derivative, d of dx, of d of dx of cos x. This is just equal to the derivative of sine x, of negative sine x rather. I know the derivative of sine x is cos x. Well, this is just negative cos x. Take the derivative of negative cos x, we get positive sine x. Take the derivative of positive sine x, we get cos x. And wow, we're back where we started. So that's the nice thing about the derivatives of cos and sine. They follow the pattern. Just make sure that you keep those negative signs in line, because otherwise it will be uncomfortable for sure. So the above solution that we got here, it says the derivative of cosine of x is negative sine of x. So we can mark that as correct. The above solution is correct. Clean off the whiteboard and send that in, and we can get it. Move into the next question on the menu. So what is the quotient rule for differentiation? The quotient rule for differentiation is very important when you are taking the derivative of a function divided by another function. So in this example, we have f of x and g of x. It gives us the general form, but I'll run us through an example just so that we can see how this general form works when it's in action. So the general form of the quotient rule, f of x over g of x, those could be any functions: trigonomic functions, polynomials, exponentials, logarithms, any function that's valid. So this is equal to the derivative of the top multiplied by the bottom, just regularly, minus the regular top times the derivative of the bottom, all of that divided by the bottom, but you got to square the bottom. If you don't square, I will care, and it does impact the calculation a lot if you have the bottom there or not. Okay, so let's run this through an example. Let's say we have d over dx. Let's say we have something like e to the x, and then we have x plus 1. So let's see how the quotient rule works in action with this. So we know that f of x equal to e of x, f prime of x, the first derivative, well, e of x, it's super simple. It is just e of x. Nice and simple. G of x, we have x plus 1. G prime of x is 1. Just simply 1. So to sub these into our equation, we have the derivative of the top, so e of x. Multiply that with the natural version of the bottom, so that's x plus 1. Minus the natural version of the top, also e to the power of x. Multiply that with the derivative of the bottom, so that's just 1. All of that divided by the bottom squared. So that's x plus 1 squared. On the top, how about we factor out the e to the power of x? These two terms both have e to the power of x. We can factor that out. To the power of x, and what's left is x plus 1, and then the minus 1. And then on the bottom, we still have x plus 1 squared. And in here, the plus 1 and the minus 1 zero each other out. So that will be e to the x times x over x plus 1 squared. Sometimes it's more reasonable to leave not to like expand that out. But yeah, that would be your answer for the derivative of this function. Looks good, feels good, sounds good, is good. So yeah, the solution that we have here is valid and accurate. Above solution is correct. Cool. So let's clean up the whiteboard and mark the solution as correct. Oh, I guess that was the last question. Time flies when you're having fun, as the old saying goes. Let me just switch my camera real fast. So that concludes all the questions that I'm going to cover today. If you enjoyed today's Q&A and would like to be notified of when we do this next, please hit the subscribe button and ring that notification bell below. And if you'd like to submit your own questions, please visit the video links or the links in the video description below. And remember to leave a like and a comment if you like the video, and share the video with your friends if you find that this was helpful or you think that this might be helpful for your friends. This has been Millan from OneClass, and I hope to see you soon. Bye now. Have a good night, and have an amazing day as well.